So in this video we're going to be looking at AS Chem 2 Equilibria. It's topic 9, just in case you're wondering where it is in the textbook. And it's quite a short unit, it's quite simple, and really just sort of builds on a lot of the kinetic stuff from before. So if you want to check that video out, go and look at my channel, links will be in the description below, as with all the definitions and stuff. So, what is Equilibria? Equilibria, whenever you see this, you should think reversible reactions. So it's just a reaction which effectively goes both ways. So if I just write out A plus B reacts to form C plus D. Now if you've never seen this symbol before, it just means a reversible reaction. So instead of writing an arrow that way and an arrow that way, it just basically gets abbreviated into that. Now what this actually means is, in context of like a dynamic equilibria, A and B react to form C and D, but C and D can also react to form A and B. And this is the whole premise of the topic. It's just how you can make this equilibria favour one side, so favour the production of C and D. Now one concept that people always seem to misunderstand about this is, you don't have to have 50% of A and B and 50% of C and D in your equilibrium mixture. I should also mention, before I carry on, that for an equilibria to be established, you have to have a closed system, which basically means you need a sealed container. You can't have it open because things might evaporate out and that would affect the equilibria, as we'll see in a little bit. So it doesn't have to be a 50-50 split. It could be 75-25 or 25-75 or like 1 and 99 or just whatever. It can be any of these things. And basically we're going to be looking at how we can change the equilibria so we can get the products and things that we want. So the main idea behind this whole topic is Le Chatelier's principle. I can never say it properly, and I think, yeah, that's about right. And this basically says that equilibrium will shift to oppose a change. Now this isn't actually the proper definition is, if a system at equilibrium is disturbed, the equilibrium moves in the direction that tends to reduce the disturbance. But I tend to think of it like this, where equilibrium will shift to oppose change. So what does this actually mean, and how do we actually change an equilibria? Well, if we have a system at equilibria, there's a few things we can do to it, and this really is sort of the same things that we was doing in kinetics, where you just can change the temperature, you can change the pressure, you can change the concentration of either your reactants or your products, like one part of the reaction or whatever, or you could add a catalyst. So how do these things affect an equilibrium mixture? Well, what I'm going to do is just go back to our little equation that I set up before. So A plus B reacts to form C plus D. And I'm going to give this a random enthalpy value. So I'm going to say delta H equals minus 90. It's completely random. And I'm just going to make it interesting, I'm just going to say that's 2B. So we have like a coefficient on the B. So we've got a negative value for delta H, so we should be thinking, oh, that's exothermic immediately. I'm just going to write in exothermic. Whenever you see delta H, if it's positive or negative, immediately you should be thinking, is it exo or endothermic, and how does that affect things? So now I'm going to start with probably the most obvious one. We're going to add a few moles of A in. So imagine we had a test tube, and it was at equilibria, and we had so much of our reactants and so much of our products, and then we added a load of A into the solution. What would happen? Well, if we look at Le Chatelier's principle, the equilibrium will shift to oppose a change. So if we had a load of A in, to get rid of A and bring it back into equilibria, we're going to have to create more C and D. So it's going to have to react with B to create C and D. So the equilibrium will shift to the right. Now at this level, at AS anyway, there's no like formulas for doing this or anything, like at A2, and there's no numerical values. You just need to know what it does when we add more reactant or more product. Similarly, if we add a load more C in, to oppose the change, it will just shift to the left and create more A and B, simply to bring the balance back. So, that's a really simple concept. Now if we move on to temperature and how this affects it, this is a little bit more interesting, because if we say for this reaction, if we increase the temperature, when we look back at our definition, equilibria will shift to oppose a change. This reaction is exothermic. So that means when it goes this way, oh, just chuck my pen away. When it goes this way, it's exothermic, so heat is produced. Now we're raising the temperature. So effectively you can think of the backward reaction as endothermic. It has exactly the same delta H value, but it's positive. The sign just like flips. If the forward reaction was endothermic, then the backward reaction would be exothermic. But in this case, the forward reaction is exothermic, so the backward reaction is endothermic. So we know that an endothermic reaction absorbs heat. So what that means is the equilibria will shift to the left because we've increased the temperature for an exothermic reaction, and to remove the extra heat that we've added, the equilibria will shift to the left. Okay, so now we have pressure. So if we imagine that this reaction is gaseous in a sealed container, and it's at equilibria, and we're going to increase the pressure. Now this is a little bit different from the other things that we've done. If you increase the pressure of an equilibria, and we look at our definition again, equilibria will shift to oppose the change. How do we oppose a change in pressure? Well, basically, what happens is the equilibria will shift to the side of the least moles. So if we count the moles up, we've got 1, 2, 3 on the left hand side, and 1, 2 on the right hand side. So if we increase the pressure, in order to oppose that change, the equilibria will shift to the right, and that is because there's less moles on that side, so they'd occupy a lesser volume, which would therefore decrease the pressure effectively. And that's what the equilibria is trying to do. All these different changes we made, it's just trying to get back to how it was. It doesn't like being changed, it likes remaining where it is. So when you change it, it will shift to one side or the other. Now I did say earlier, a catalyst, but that was a bit of a sort of trick question, because when you add a catalyst to this, it does not affect where the equilibria lies. It doesn't mean it lies more to the right or more to the left. All it means is that the rate of reaction increases. So the equilibrium itself will be reached faster, but there will be no change in where the equilibria lies. And they do like asking this in exams and stuff. They're like, oh, why would a catalyst not make any change? And you're like, oh, well, it doesn't affect where the equilibria lies, it just affects the rate of reaction. Okay, so once again, I have the June 2014 past paper, and we're just going to run through it for some real life questions that you'd actually get asked. So it actually turned out this is on the first page. So a dynamic equilibrium is established when gas A is mixed with gas B at a given temperature. Show how the concentration of reactants and products change over time. Okay, so this is a graph I haven't actually been through, and question 1A asks, on the appropriate axis on figure 1, place an X to show the time when the equilibria is first established. So what does this graph mean? Because I ain't actually been through it, so I feel like I should explain this properly. Well, we have time and concentration on the Y and X axis, and effectively what we've got here is, this is the products and this is the reactants. So what's happened is we've put two products in a test, we put the products and the reactants in the test tube, well, just the reactants in the test tube, and over time they've reacted and formed the products. So that's why as this goes down, this increases. So they're reacting, and that causes them to be used up, so there's less of them, and as they've reacted, they've formed C and D, so there's more of C and D, so that obviously increases. And this, the products usually start at the origin, just because obviously they start with none. You just put A and B in a test tube and that's it, or wherever you're doing it, in a container or whatever. So they tend to cross over at a point, and many people seem to think that this is where the equilibria is established, but it's not. Because when we look back at sort of what an equilibria actually is, it's basically where the forward reaction, if you ever get asked for what the equilibria is, the forward reaction equals the backward reaction. And that's vital. So, it's the point at which the forward and the backward reaction remain level. So as you can see, it's roughly about here. I'm just going to get my ruler. It's about there, where they've started levelling off. So on these graphs you want to be looking for the point where it levels off, and that is where you have whatever it's asked. What's it asked us for? Show X. This will be like point X. So if I just get my pen out, which I can't actually find, we can write an X there. And this is the time at which the equilibrium is established, where there's no more C and D being made and no more A and B being made. They remain at constant levels, but they are still reacting, but it's just at a constant rate. So C and D is forming A and B are forming C and D, but because it's happening at an equivalent rate, the concentrations just remain constant. And that is effectively what a dynamic equilibria is. So for question 1 AII, state how the rate of forward reaction and the rate of the reverse reaction are related to each other at equilibria. I've already said this, the forward reaction is equal to the backward reaction, so the concentrations therefore remain constant, and that's all you need to write for the mark. Give the meaning of the term dynamic in the context of a dynamic equilibrium. Now this used to trip me up, because I didn't really get what dynamic meant. But dynamic in and of itself means that although the concentrations of an equilibrium remain the same, there is still a forward and backward reaction occurring, but this happens at the same sort of speed. So the answer to this question is the forward reaction and backward reaction occur at the same rate, therefore meaning that the concentrations remain the same, but a reaction is still occurring, but obviously you don't notice it because there's one's being produced, the other's being produced. Question 1 CI. The total pressure on the system is increased at a constant temperature. State and explain the effect, if any, on the change on the position of the equilibrium. Whenever you see these where it's like, what's the effect on this? Always just flip over, have a look back at the actual equation. So we know it's pressure, so the equilibrium will oppose a pressure increase by moving it to the side of the least moles. So there's 2 moles of reactants and 2 moles of products. Oh wait a minute, same moles. That means there won't actually be an effect. So we can say there's no effect. Why is there no effect? As there is an equal number of moles on both sides. So it's really as simple as that, and there's your 2 marks. Now 1 CII, this one's a bit more tricky, bit more evil. State and explain the effect, if any, of the change on time taken to reach its equilibrium. So this is the continuation of that. So basically it's asking, the pressure's been increased, how will this affect the time taken to reach equilibrium? If you ever think back to the kinetics video I did, or just your kinetics knowledge, I'll put a link to that in the description as well. It's basically like a kinetics meets equilibria sort of question. So as we increase the pressure, the volume decreases, and therefore there are more particles in said given volume, and therefore more successful collisions. So we know that it decreases the time to reach equilibria, and for the explanation I've already said it, it's that there are more particles in a given volume, that would be 1 mark, and therefore more successful collisions, that is the 2nd mark. Or you can say there's like more frequent collisions or something, but you can write it different ways, but as long as you get the core concept, you will get the marks for it. So that's as simple as equilibria is really. It's not that complicated. They might tie it in with kinetics, and to be fair, they like doing that in chemistry. They'll tend to throw in a question somewhere where it'll be on another subject but relate to what you're doing, and it's no different. It's just, you've just got to tie all your knowledge together and then you'll be alright.